Okay, so welcome back to another video. In today's video we have the following question. Given that if P sub n is the product of the terms in the nth row of the Pascal's triangle, we want to evaluate the limit as n approaches infinity of P sub n minus 1 times P sub n plus 2 divided by P sub n squared. And so I drew a little diagram of what Pascal's triangle is designed as. It's a triangular array given with the numbers are defined as the binomial coefficients. Hence, this is why Pascal triangles is actually useful for binomial expansion. So as you see, this is actually given with, for example, x plus y to some power n. X plus y really doesn't matter in like that general case. It's more the exponents. Depending on your n value, this gives the expansion out. So we have x plus y, for example, like quantity square. So n is equal to 2. So here we have that the second row right over here is that it gives obviously we know with the quadratic expansion gives out the three terms, x plus y is x squared plus 2xy plus y squared. Then the coefficient is defined such that so 1 correlates with x squared, 2 correlates with x times y, and then 1 correlates with y squared. And then depending on whatever your choice value of n is, this is the binomial coefficient as follows. In other words, it's actually another definition of the combination of n choose k. And so, given with Pascal's triangles, we have P sub n is the product. So in other words, we want to calculate the product of the nth row. So what would that be like if we were to put this in terms of limit P sub n minus 1 times P sub n plus 1 and then divide by P sub n squared. And so that's pretty much the gist. Pretty much we can see that we have to put this in terms of a product series and then rewrite this. Basically, eventually there's going to be some sort of induction, and I'm not really going to prove the induction part because you can see this for yourself clearly, but if you want to prove that as an exercise, feel free to. Rearrange using some algebra, and then that actually gets us to the limit that we want to achieve. So other than that, let's actually just jump in. So obviously, we would know that Pascal's triangle, it actually gives out the summation specifically for n equals, your index is n is equal to 0 to k of some choice n choose k is actually defined as, not for example, it's defined as n then choose k. Then there's a general formula follows that it's n factorial divided by n minus k factorial and then multiplied by k factorial. It's a combination, in other words. So that's the definition, the formula for our combinations from there. That's how, hence, we get these binomial coefficients. But we see that it's multiplied with x to the power n minus k times y minus yk, and that's how we get those binomial expansions with the n exponents here defined as follows. But we're not really going to pay attention to that. I just want to give just some sort of like intuition of how that's usually defined the way we see with Pascal's triangle specifically. But since we're asking, it's asked us for P sub n as the product. So any sort of product from the nth row, we want to calculate that product of the row. So we have, for example, n is equal to 4. P sub 4 would be 1 times 4, 1 times 4 times 6 times 4 times 1. And so obviously that's just equal to, 16 times 6, that's 96. So that's basically the way we want to do it. And so hence we have the limit that we want to evaluate. So we have this. So now let's actually start with some generalization. We'll call this P sub n. And so P sub n, of course, is the product of those terms in the nth row. So that means it has to be in the form of a product series. So here we have n, some partial sum n. We're going to start with that. And then k is equal to 0 of some n choose k. In other words, you can see that this is just, so for example, n, and then you start with the index k is equal to 0, then multiply n1, n2, and then keep going on so forth all the way up to nk. In other words, you can say that this is actually just substitute our definition, the partial sum k is equal to 0 of n factorial and then divided by n subtract k factorial times k factorial. All right, so now let's actually expand this out a bit. So what we do this is just all the way up to the nth term. So we have n factorial, then divide this with n minus 0 factorial, then 0 factorial, multiply with n factorial, then n subtract 1 factorial, 1 factorial. Then we just keep going, so on and so forth. Then we go up all the way up to n factorial divided by n minus n factorial, and then times n factorial, like so. What we can do is we can actually find that little generalization saying that, so we can actually rearrange the terms since everything is in terms of products, so it's associative. So what that gives us, we can actually rearrange this. Well, specifically first we have n factorials on all the denominators. We just factor that out. It's actually just n factorial, then to the power, so n plus 1 times, so over here, then multiply with, of course this is still our product series, our partial product series, then rearrange the terms. So we would have, so let's see, we would have, so here we have n minus n factorial, so that's 0 factorial. We can move the 0 factorial here, then n minus 1 minus n, or n minus n minus 1, so that's just actually 1 factorial. That can just move inward over here. We, again, rearranging the terms, interchanging. So what it gives us is that we have 1 divided by some k factorial square, since it's double that, the product. So that would be 1 divided by k factorial square. So that's our little generalization for p sub n. Now the next part is it's just p sub n plus 1. What is that? What you can do is you can actually just use the induction to show this. But again, I said that I was going to skip that step. Then you can verify this yourself if you want to. But when you plug n plus 1 back for to the generalization over here, we have that this is just n plus 1 factorial, then to the power n plus 2. Then to the index n plus 2, or excuse me, that's supposed to be n plus 1. Then k is equal to 0 of 1 divided by k factorial square. So now we have that. So let's actually, we have our pieces. So now let's actually perform a little division over here and then use some algebra to solve. Let's start, given we have p sub n minus 1 and then p times p sub n plus 1, then pn square. Let's just start small and calculate or simplify p sub n plus 1 divided by p sub n. So let's see, when doing this, we just substitute whatever we have. So p sub n plus 1, we said that this is n plus 1 factorial, then n plus 2, then multiply with the product series, k is equal to 0 of 1 divided by k factorial square, and that's being divided by whatever our p sub n is. So this is just n factorial, then n plus 1, then we have the product series, the partial product series, k is equal to 0 of, so 1 divided by k factorial square. Actually, this is supposed to be a n plus 1 on the top over here, like so. So keep going further. What we can do is we can actually perform a re-index specifically for our product. That's the index all the way up to n plus 1. So what I can do is that I'll just evaluate whatever n plus 1 into that series is, then multiply that with the product that ends at n. And so what you'll notice from here is that the terms will actually cancel out. So let me actually just rewrite this in full before I see this, before you guys see the bigger picture. So n plus 1 factorial, n plus 2. Then we have 1 divided by n plus 1 factorial square. Then multiply with the product n, k is equal to 0 of 1 divided by k factorial square. Then I just divide this with n factorial, then n plus 1, multiplied with the product n, then k is equal to 0, and then 1 divided by k factorial square. Okay, and then you'll notice the product series will cancel each other out. Then if you just simplify this, you just combine the products together, you notice that the 2's for the exponents will cancel, so it's just left with n on the top. So let's see, we just keep going further. Then, so if we keep going further, then we have n plus 1 factorial, then to the power n, divide this with n factorial, then to the power n plus 1. Then we keep going further, notice that the factorials over here, I can actually, since there's exponents, so you're distributing the exponents to each of the products, so n plus 1 times n, then n minus 1, you just keep going so forth. It's just basically we're simplifying stuff. So let's see. So if I do this, so I'll just factor out the n plus 1, then distribute the exponent n. Then we can just keep going with the factorial, so n factorial, then distribute the exponent n, then n factorial, then n plus 1. Simplify this out even further. So this, let's see, we subtract the n's. So it's just n factorial on the bottom, and then it's just n plus 1 to the power n, and then divided by n factorial, like so. So now the other thing left to calculate is, I'm actually going to use the same marker again. So the next thing to calculate is our p sub n minus 1 then times p sub n, since if you combine the products then we will actually achieve what we're trying to look for. So let's see. So p sub n minus 1 then divided by p sub n. So I'm going to skip the work. I'll let you try this as an exercise to calculate the algebra to this. It's basically doing the same method that we just showed over here. But in other words, once you actually get to the wire, you'll see that p sub n minus 1 divided by p sub n is actually just going to equal to n minus 1 factorial, and then divided by n to the power n minus 1. So now the next thing we need to do is just calculate these two products together and take its limit. So let's switch on to the next marker. So now the limit as n approaches infinity of p sub n plus 1 times p sub n minus 1 divided by p sub n square, okay? So when we do this, let's actually just combine these two terms over here, one here, and the other one over here. Like so. So let's see, so we have, that would be n plus 1 to the power n, then divided by n factorial, multiply with n minus 1 factorial, then divided by n to the power n minus 1. So what you'll notice is that if we were to expand n minus 1 factorial, so it's n minus 1 times n divided by n, or actually I set it backward, it's supposed to be this expansion. When you expand n factorial, so it's n then times n minus 1 then n minus 2, basically in other words n times n minus 1 factorial, so the n minus 1 factorials just cancel each other out. So you'll see that this is just well, I'll write that limit part later. Let me just actually put the algebra first before we continue forward. But actually, you know what, I'll just write the limit. So this is the limit as n approaches infinity. So the n minus 1 factorials cancel each other out, so we're just left with n plus 1 to the power n, then divided by, so it'll be n then times n to the power n minus 1. We just keep going further and simplifying. So that means the minus 1 will just vanish. So we have n plus 1 to the power n, then divided by n to the power n. Just keep going. They share the same exponent, so I can just group this together. So in other words, I can just write this as n plus 1 divided by n, then to the power n. Simplify it further. We have that this is the limit as n approaches infinity of, so this is 1 plus 1 divided by n, then to the power n. But what's interesting is that this is actually the limit definition of the constant e. So therefore the final answer is that the limit as n approaches infinity of p sub n plus 1 times p sub n minus 1 divided by p sub n square is just equal to e, like so. And there we have it. Final answer drawn in the black box. Actually comes down really nice. Seriously though, yeah. So that's pretty cool if you ask me.